Yeah, I actually broke a toe in August, my little toe, of all the crazy things, and it caused more trouble than you can possibly believe. I ended up having surgery and a pin stuck in it. It was stupid. I slipped down a step. Anyways, so have you ever been in a situation where you've discovered something really, really cool, and you're dying to talk about it with somebody, and everybody around you, your friends, your spouse, none of them have a clue, and you'd have to talk to them for 2 hours before you could even get them up to speed enough to tell them what you found that was cool? That's why I'm excited about this presentation, because you guys are actually going to listen to me, and I get to talk about something that I really love. So very cool. This presentation is actually a combination of a couple presentations that I've been trying to figure out. They're like half presentations, and I put 2 of them together and ended up with 1.5 presentations. So I have no idea how this is going to work out, but there's a part of this which is taken from a presentation that I gave at Java 1 3 years ago now, 2013, on JVM internals, introduction to JVM internals. So we're going to cover that. So hopefully that's of interest to you guys, figuring out what a JVM does and how it works. Then there's another piece which is more vision, which is like, where is the JVM now, and where is it going, and where do I think it's going to go? And some really cool work that's been going on in a couple different places in some really neat technology. So we'll get to that. Final point before I get started is that I am an employee of Azul Systems, but the views that are presented here are not necessarily those of my employer. So anyways, yeah. So this is not an Azul pitch. This is definitely technology. Go. Oh, I've still got Freddy's malware up here. Hang on.
Hit escape.
Thank you. Told you. Okay. Here, let's just try this.
Command F.
If I get the cursor here and try this. Ha! I'll have to debug this later. Okay, so right, moving on. So this is kind of what we're going to cover today. We're going to talk about the virtual machine model. So that's basically what a virtual machine is supposed to do, and this is drawn straight from the JVM specification, which gets updated pretty much every time they come out with a new JDK. But there's a lot of it, of course, that doesn't change. So we're going to go through some of that. I'm going to pull some cool bits of technology out of existing JVM implementations just to show you how some of the things that are specified by the specification and the model actually get done in real life. Then I'm going to go on probably a rambling talk about technology evolution and some of the things that I've seen in my long career and how that has an impact on what's happening in JVM technology. And then finally, I'm going to talk about that cool research that's been going on that I think you guys will find interesting. Already covered this, I think. Yeah, spent time at Oracle fixing bugs in Hotspot and JRocket. In fact, the guy who's coming 4 weeks from now, Marcus Hurt, was part of the BEA team that developed JRocket. So, in fact, that tool that he's going to talk about was actually surgically removed from JRocket and patched onto Hotspot just a few years ago. So that's it. I'm going to clear my throat. Hang on. That never works out well. Okay, so just to clear up some terminology. So JVM is the execution engine of the Java runtime environment. And so I hear a lot of people throwing around these 3 terms, JVM, Jre, and Jdk, almost interchangeably. And probably the worst one that I often hear is when people talk about the Java class library as the JDK. It's even done inside Oracle. It's not technically correct. The JDK contains the runtime environment as well as this collection of tools, which is the Java compiler, the Java debugger, all those things that are in /bin. The class library provides the APIs that you use in your programs. all those handy stuff, collections and I/O streams and stuff like that. So those are the pieces. Is this like news to anybody? Embarrassed to raise your hand. Okay, I get it. All right, so rough starting point for the JVM model. You have a Java application on the upper left there. It takes advantage of the Java class library. Both of them exist in Java space. They're compiled classes that contain bytecodes and classes and all that kind of stuff. We're going to talk about that in a minute. They run on a program called the JVM, which is a native program. It executes and is made up of native instructions for the CPU on the host that it's running on. It, of course, takes advantage of operating system services. So there's a distinction there between Java space, user space, and then the place where the kernel lives. Okay, so how do we get a Java program to run? We start out with source files, which are in Java or other languages. They get fed through a compiler. Outside, they produce class files. Those class files can sometimes be bundled into larger files called jar files, and the JVM knows how to load those in. You tell the JVM what your class path is. That tells it where to find class files, and you can load them in as needed. So focusing in on the first part of that, so Java compilation takes a piece of Java source file and basically translates your textual features of your program into binary encoded things inside the class files. And there's actually pretty close to a one-to-one mapping. The only thing that's a little bit unusual is this thing called a constant pool at the bottom, where they gather together all the references from a method to a field, or a method to another method, or a method to another class, and they put them all in this centralized place, constant pool, so that it reduces the size of the bytecode, and so that all of those are, because several methods might use the same external class, or might call on the same external method, so it saves space. And then, of course, constants go in there as well, so that bytecode is kept small. You don't have big, long 8-byte floats stuck in your bytecode. And a single source file, this diagram is not technically correct because a single source file can actually produce multiple classes. So if we did this right, there could be several class files. You could have inner classes and so on, which compile out to independent class files. All right, so class loading. So now we've got a class file, and it's got all this binary encoded stuff that came from the features of your program. And the operation of class loading basically pulls this into internal data structures. And every JVM encodes these differently. There's sort of a different emphasis on how class structures work and how they all link together. Emphasis, of course, is on performance, so that as we're going through and executing our program, we can access these things as they're needed at runtime very, very quickly. And this, if you're still using a JVM that has a permgen, this is the stuff that goes into permgen. You'll often hear it called metadata. Heard the term? Okay. Okay, here's some of the phases of class file preparation. The first phase is what we just talked about. We parse the binary data from a class file into the internal data structures, setting them up in a convenient way so that we can access them quickly at runtime. Verification step. This is a pet peeve with myself and some of my former colleagues at Oracle. Somebody in the WebLogic group once upon a time thought it would be a good idea that it would make WebLogic run faster if they added an option called, have you guys ever heard of this, -x verify none? Anybody? Don't use that option. Don't turn that off. It causes crashes. Anyway, so verification will actually go through the bytecode. It'll confirm a bunch of stuff. It'll confirm that the types match up. It'll confirm that you're not going to overflow the stack. The stack remains balanced between invocation and exit of a method and so on. Linking is a step where we get the class ready to run. We optionally can load some of the classes that it refers to and bring those in. In practice, although all the commercial JVMs do this lazily, so they'll do that as they're accessed at runtime rather than in advance. And then finally, we atomically run static initializers. So if two threads are loading the same class at exactly the same time and trying to initialize them, only one of them will run the initializer and the other one will wait until it's done. So a class always gets initialized exactly once. All right. So this is the model of a Java thread. Java thread is a series of Java frames, which corresponds to a method invocation. And a Java frame contains some of the things that you see here. Now, in practice, of course, this is done in a much more compressed and efficient manner, and we'll talk about that in a few minutes. But a Java frame contains an operand stack. Java is, at its lowest level, a stack-oriented, hybrid stack-oriented architecture. You push operands onto a stack, you perform operations on them, and you pop them back off. The reason I say hybrid is because pure stack-oriented architectures just pop between memory and the stack, and Java actually provides local variables, which is unusual for a stack-oriented architecture. We also have an array of parameters and locals, so those are the parameters that are passed into a given method, and then the local variables that you'll need to execute that method, and the other obvious stuff. Index of the next bytecode, that's roughly equivalent to like a program counter at a hardware level, so it points to the next bytecode that we're going to be executing at every point in time. So as Java frames are stacked up, then we can return back and go exactly to the right bytecode that we left off at. Make sense? Is this way too low level for anybody? No. Okay. Sorry?
I'm nerding out. I don't know about it.
All right. We got one person to nerd heaven. All right. So now we'll go through execution of a couple of bytecodes. I can't go through all of them. There's a whole bunch of them that are just stack operations, pushing and popping, and arithmetic operations, logical operations on things that are actually on the stack. But there are some that are kind of interesting because they take advantage of some of the other parts of the Java, what we call the runtime system. So for example, the new bytecode. If we're creating an object of a particular type, the new bytecode will have a bytecode followed by an index into the constant pool. And the index into the constant pool will resolve to actually a class structure, a class reference structure. And this is not a mistake. You'll notice that the arrow goes into one entry on the constant pool, and we actually get a string out of another arrow. That's because there are actually internal references inside the constant pool. So you'll have a class reference, which will have an index, which will point to a string, which is the name of the class. And we'll go through, the next bytecodes we'll go through do this a lot. So you notice you end up with a string. You don't end up with a pointer to a class. You don't end up with anything interesting. You don't end up with anything binary. So the Java JVM specification leaves it as a task for the JVM to figure out how to map this string to the actual class that it needs to run. And what commercial JVMs do is they actually will load that in on demand. So the first time you access a class for the first time, then that'll get loaded in, this will get resolved, and then we'll save away a pointer to the real binary data, and next time we come through and create perhaps another instance of this object, we have a fast way to get to the class data. Okay, operations with fields, static fields, or instance variables. So get static and put static obviously have to do with class variables, static variables. And then get field and put field are the operations, or the bytecodes that operate on instance fields. And so again, it's the same structure. We have a bytecode followed by an index into the constant pool. The entry in the constant pool will be a field reference type, and it's going to have a couple of indexes that point to other pieces of the constant pool, which are actually strings. And once again, it's left to the JVM to figure out how to map these three strings, the field descriptor, the field name, and the class name, into the actual field in the real class and figure out where that actually lives in the object that we're accessing. Okay, so far so good? All right, one more. So when we invoke a method, And again, this is very similar. Invoke static invokes a static method. Invoke virtual is an instance method. Invoke interface, it's fairly obvious. And then invoke special is for constructors and class initializers. So that's used only in special circumstances. There's one that I don't have on here, which is the newish one, invoke dynamic. And that uses a completely different structure, so it wouldn't work here. But, and quite frankly, I didn't understand it myself. So there. I've said it. Yeah, right. He may be the only guy. Anyway, so once again, we end up with a bunch of strings. JVM's got to figure out how to map those strings to the actual thing that we're going to operate on. JVM specification says a couple things about the heap. The heap contains all class instances, so every time you do a new and create a class instance, it ends up on the heap. You guys probably all know what the heap is. Heap is created on JVM startup, shared among all threads, although almost all commercial JVMs will actually slice the heap up into pieces, generations, and also thread-specific areas so that threads can allocate objects very quickly without contending with other threads. It is legal to actually contract the heap, although none of the JVMs that I have worked with ever do this. And then finally, you need some method of reclaiming space when it's no longer needed. JVM specification is actually very, very quiet on how and when this is supposed to be done. And frankly, it is legal for a JVM to run completely out of heap, but it run completely out of heap, stop everything, and then go through, trace through all the objects, figure out where the free memory is, maybe compact if you need to, and then proceed. And in fact, that is a fallback mechanism for a lot of the garbage collecting algorithms that are out there. Monitors or synchronization. So this is just a slide that quickly shows how that's actually translated into bytecode. So when you do a synchronized method, it's actually equivalent to synchronized on the object, this, that we're actually running in, and then that gets translated into the bytecode that's over there. A load 0 simply loads the reference that's in the 0th slot of our parameter array. Then we do something, we monitor exit. Now, the tricky thing about this is this looks nice and clean because we're using a block structured language. The JVM specification actually says this doesn't need to be this way. You can actually do a monitor enter in one method and then go off somewhere and do something else and actually do the corresponding monitor exit in a different method. Nobody does this, of course, but it means that JVM designers have to handle that because in order to handle any bytecode language, they have to be able to handle that kind of event. So it makes things more complicated. Yeah.
What would the code look like to do that?
You can't do it in Java.
Can't. Oh, okay.
Yeah, it's inexpressible in Java.
Got it.
Oh, sorry. Yeah, Bob asked, what would the code look like to do that? And
Are there other JVM languages that do support that, or is it?
not that I'm aware of,
Okay.
but the JVM has to be designed in such a way to handle it, which complicates things enormously. Similarly to like goto, you don't actually have to have structured loops in the bytecode. You can wander all over the place, and the JVM's got to be able to handle that without actually throwing up. Okay, so how's that feel to you guys? Get a good sense for what JVM actually does? Nodding, good. All right, so let's look at some of the ways these things are done. So when you talk to a JVM engineer, they'll inevitably talk about these three primary subsystems, and they'll probably claim to be an expert or a worker in one of these three subsystems. Memory management, although typically people just say GC, but it actually covers not only collection but also allocation. And obviously allocation and collection are intimately related. Compilers, where you actually take method bytecode and compile it down into native language. And there are just-in-time compilers that are typically designed to be very, very fast. So if a method is discovered to be either needing compilation or deserving of compilation, you do a quick and dirty compilation into native. And then there's an optimizing compiler often. Hotspot people call it C2. And that's a much more complicated, much more intensive kind of thing where it will actually look at not only the method that's being compiled, but methods that it gets called by and methods that it calls to figure out if it's actually a candidate for being inlined or for inlining something else. Does anybody know compiler terminology? So it converts everything into SSA form. There you go.
I was going to say, can you explain inlining just in case?
Okay, so inlining is where you take a method that calls another method, and instead of actually having a call there, you'll actually take the code that would be in that called method and stick it right in line with the calling method. And that saves the cost of actually doing the, creating the stack frame, calling out to something, returning from it, restoring the stack frame, and doing all that. So it's actually a huge speed up.
I got a question on,
Sorry, what? Sorry?
So it's copied to the data method?
Yes. And there's other things that need to be due. Sorry, she asked if it was actually copied. The call-led method copied into the calling method, and yes, it's partially what happens, but actually, before you even do that, everything will get converted into this intermediate representation, be all these transformations done, and by the time you're done, it doesn't actually look like the call-led method anymore, because registers will be reused and stuff like that. Sorry, you had a question?
yeah, I just had a question, like for a higher level design, if you're doing like trying to do a pure function approach on a method, does that impact how often something gets inlined or how efficient that is? Just saying, because if it's copying an entire method call, if it's a pure function at a higher abstraction, would that have any effect there?
In practice, what Hotspot does and what Zing, the JVM that my company produces, does is it actually counts the number of invocations. It's a fairly simple way of looking at how frequently something gets called. And when something reaches a particular threshold, then we'll kick off the optimizing compiler and say, here, take a look at this. And that's when it'll consider not only who calls it, but what it calls, and whether that also has been called enough to say, okay, it's worth it for us to pile that in line. And there's a storage cost and so on, yes.
Does that have any impact on like debugging and traces as it relates to the stack? Or?
That's an excellent question. It does not. Sorry, yeah. You know what, I'm supposed to be tossing this thing around.
Yeah.
It's like 3D in front of the camera.
Yeah.
So I was just asking if that had any impact on debugging and traces. Like if you're looking at a stack trace but it's inline, I would imagine that metadata is being somewhat passed around at a higher level.
Yes, exactly right. So from a Java debugging standpoint, and it's one of the other things that the JVM has to figure out, from a Java debugging standpoint, even though you're missing one or more frames in the native stack, the Java debugger has to pretend that those calls have actually taken place. And if you actually look at the local variables that get passed from one method to another method, even though that method's been inlined, it's got to pull them out of wherever they are and be able to display them. So somebody's going to get hurt here.
So how does that affect, I know an internal API they added in Java 9, the stack walker. How would that affect your calls to look, reading up the stack? Like for instance, a lot of the JDK classes are using it for security checks, for instance.
So once again, the JVM has to maintain the illusion that that all of those Java calls have actually taken place. So when you do a stack walker, it actually has to put those back together and feed them to your program and say, yeah, sure, we called that thing. Yeah, of course we did. Why do you ask?
Good answer.
This could get bad. There was something else I was going to say. I don't know. I lost it. Okay, we'll get back here. Okay. Oh, the other thing that's worth mentioning is this runtime component, which is basically the catch-all for everything else. Everything that's not a garbage collector or a compiler, the JVM engineers will call runtime. But there are clean interfaces between these components, and that's what allows you to, for example, turn off one garbage collector and use another one. Or in the case of Zing, we actually have a couple different compilers that you can actually pick from depending on the nature of the code that you've got. All right, so did that cover everybody? Questions on compilation? I mean, that's really a whole presentation all its own. Yeah.
I can just speak loudly.
All right.
So is there any optimization done, or is there any difference in the way something's compiled based on whether it's compiled before or during the runtime? Like if you're using the compiler library inside of JDK?
You mean compilation of Java code?
Like
Yeah.
just in time
Yes. There are often several levels, and in fact, later version of Hotspot now has sort of variable optimization. So the quick and dirty compile that's needed, for example, to make a method that's being called over and over and over and over, and you just want to compile it and speed it up somewhat, well, we then, in the background, will go through a deeper optimization analysis. Yes, that code looks significantly different. Because the optimizer will do all kinds of, well, here. Let's go back. So some of the things, I mean, I explained inlining. Box unbox is an operation where you're actually putting data into an object, and then you call another method or someplace else, and you pull the data out of the object either through getters or whatever. And there's a process called escape analysis to figure out if anybody else actually gets a pointer to that object. And if it does not, then there's no need to actually create the object, go through the work of allocating heap space and actually creating the object. And instead we'll just pass the scalar values, the primitive values that are the components of that object around. And that can be done by the optimizing compiler. It'll just say, we don't have to, capital I integer is a very common example, where you're calling a method that actually is looking for a capital I integer, and so you actually have a primitive integer in your routine. You box it up in a capital I integer, you send it to the routine, and inside the routine all it does is unbox it again. So when you actually do an analysis of that code flow, you find out that, oh, boxing it, unboxing it, skip that.
So does that negate the need now? I've seen a lot of primitive hash maps created to avoid boxing and unboxing. So does this avoid the need for those primitive hash maps now?
Not necessarily, because the hash maps are keyed off object references. So you actually have to have a boxed object for those. So yes, those do still have value. Good question. Did everybody hear the question? Do you still need, there are new hash maps in there?
Can you repeat it real quick?
Okay, so there are new hash maps that can use primitive data types as keys instead of actually objects as keys, as way it's always been. And so her question was, well, does the optimizing compiler eliminate the need for those new hash maps? And the answer is no. The old hash maps actually still need an object reference. That's what it's actually hashed out from. Optimize loops. So if you have a finite loop that always rolls through 10 times, for example, one of the things you can do is actually unroll the loop. So it's all done in line, and you actually do iteration 1, iteration 2, iteration 3, so on and so on. Now there's a whole bunch of them. Sorry?
Smoke and mirrors.
Yes, that's right. All this stuff happens behind the scenes. But it makes debugging JVMs very, very interesting, I can tell you. Okay, so taking that diagram that we had earlier in the JVM model and exploding this a little bit, the JVM is native code, but you may or may not be aware the JVM is actually implemented as a native library, a native shared library. If you look through your file system, you'll find something called libjvm.so. That is the actual JVM. The thing that you call, typically Java, the Java executable, is actually a very small program that attaches this native library and then jumps to it. And the reason it's done that way, of course, is so that other native programs can actually embed a JVM in them. And there's a well-defined interface between native code and the JVM that allows it to, for example, create objects, invoke methods, that sort of thing. And vice versa. That native interface also allows the JVM to call out to native code And that's how things in the Java class library can actually get through and talk to the OS. So if you create, for example, a file, capital F-I-L-E object, and you open it, well, obviously that can't be done just inside the JVM. Somehow you got to get out to the operating system. And the way that's done is the code in the Java class library will actually talk to a native library, which will then talk to the operating system. Clear? All right. Let's see, what did I forget to say? And so to actually make that happen, has anybody here ever written JNI code? A couple, all right, impressive. So there's a naming scheme that allows the Java class library, or the JVM, to actually find these routines down in native land. So when you see something in the Java class library, if you're ever looking through this code and you see something that's a method that says native, it's got the keyword native on it, that's a key for the JVM to actually look for a specially named function down here in native land. Okay, so from a JVM's point of view, there's actually three kinds of objects. There's, Hotspot actually calls it instance class. I like to call it loaded class. So an object that is created from a class that we've loaded, that you actually loaded from a class file and you've created an instance of it, that's a loaded class. And what the features of that class is that it will have instance variables that could be a mix of primitive types and reference types and arrays and so on. So that can all be part of of a loaded class. A reference array class is an array that contains only references. So if you create an array of objects, for example, that's an array of references to objects. And finally, a primitive array class is an array that contains only primitives, an array of ints, for example. And the reason that it's important to distinguish between these is because, number one, they're laid out differently in memory so that the JVM can access them efficiently as you're going through an array. And secondly, as you're doing garbage collection, you need to know whether, so for example, collecting a reference array class is a very, very straightforward operation. You just click through all the elements of the array. Collecting through a loaded class is different. You actually have to go to the class and find out, okay, which of these fields are references and which of them are primitives, and then you can trace through the references. And then primitive array classes, you have no work to do at all. All right, so a loaded class. So if we have an instance of a class that we've created, and I have here a diagram, we have a class A, which defines a field called A. Could have thought about that one a little better. Sorry. And so that objects of that type will have an object header, call it 8 bytes, and then they'll have this field A. A subclass B tacks on 2 additional fields, B and C. Again, questionable naming, but so those will actually occur at offsets, at different offsets. And the point of this is that the JVM, when given an object of type class A, or any of its subclasses, knows exactly where to find, for example, field A. Field A is always at offset 8, okay? Because even subclasses will still maintain field 8, or field A at offset 8. Okay, so that way JVM doesn't have to go hunting around and find the class object and say, oh, good heavens, where in the world is this field that I'm looking for? It's always at offset 8. This is actually sort of the same scheme that C++ uses when it defines objects and subclasses. Similarly, for instance method dispatch. So one of the features of Java is that you can override, a subclass can override an instance method of a superclass. So every class has a thing called a vtable, and a vtable is just an array of, and it's actually also like C++, just an array of references to functions. And so class A actually has 2 functions, method 1 and method 2. Class B is going to extend class A define a new method, method 2, or override method 2, excuse me, and then add a new method, method 3. So the vtable for class B has 3 entries in it instead of just 2, and its entry for method 2 points to its own implementation. And very similarly to the way that the JVM can find instance fields at a particular offset, JVM now knows every time I'm calling method 2, regardless of whether I'm calling it on a class A or a class B or any other subclass of class A, method 2, whether overridden or not, will always occur. We'll always find a pointer. Always find a pointer to it in the second entry of the vtable for that class. Yes?
Are like the vtables and field offsets, are those kind of standardized or are those implementation specific?
They're implementation specific, and I've actually simplified this. In Hotspot, for example, and in Zing, because there's both an interpreter and a compiler, every method has both an interpreted version and a compiled version. And so when you actually looked this up in the vtable, there's actually 2 entries. So to your question, no, every JVM does it slightly differently. Good? Make sense? All right, so we've talked about this a little bit, and I just mentioned this. So there's 2 different ways of execution. You can either run through an interpreter, which actually reads the bytecodes one at a time, executes them, and then reads the next one. I say that with a caveat. The actual interpreters that are in modern JVMs aren't actually of this simple loop, read, execute, and so on. They'll actually use bytecodes as an index. This is going to take us back. Any fourth fans here? FORTH? Okay. Remember direct threaded code? Sort of, kind of. Anyway, so the point being that as you're executing the native code that does a bytecode, it'll actually jump to the first instruction of the native code that implements the next bytecode. You don't actually have to do this loop switch sort of thing. It's all kind of done in line, and it speeds up the interpreter. An interpreter is optional. You don't actually need an interpreter in a JVM. You can actually compile methods on the fly. And if anybody's actually used JRocket didn't have an interpreter. It used its fast, just-in-time dirty compiler to get that first compilation done, and then you could execute it directly. All right, digging farther down here. Okay, so the diagram that we had a few minutes ago that showed the stack of frames in the JVM model, and each frame has to contain certain data elements. This, in practice, is how it's actually implemented on a real JVM. So this is a native stack that you would normally use for calling functions. But the JVM is actually going to pack some things on here that make execution of Java code handy. So you will recall that every frame has to contain an array that has the parameters that are passed to the method, as well as the locals that are used by the method. And then before we call a new method, let's see, where are we? Oh yeah, okay. So stack's growing up. So as this frame is executing, it's actually popping stuff on and off the operand stack here. And the way the JVM specifies that parameters are to be put onto the stack for invocation of the next method. So this operand stack here has actually packed these parameters on here, and then the JVM will look forward, see how many local variables are actually needed for that called method, the one that we're about to call. It'll allocate the stack frame. Then it'll actually do the function call. So inside this native frame data will be stuff like a return address, a native return address, a frame pointer, the kind of stuff you'd normally see in a native frame. And then this was the other stuff that was in that Java frame box, the bytecode, the next bytecode to be executed, the method, the class that's currently be executing. All that stuff gets stuck in here. And now our new method here for frame I, is actually operating with a brand new operand stack all its own. So that way you can take what's actually a relatively confusing stack structure and compress it all into a single linear stack inside the JVM. And did I miss anything? No. Okay. It's a good place for a break. So that's everything I was going to say about JVM implementation and JVM technology. Any questions? Anything that, yes?
Just to clarify, the last thing you said the bytecode is in the native stack, in that Java frame data.
The bytecode index.
Oh, the bytecode index. Sorry.
Yes. So that would be the index. The previous frame is doing stuff down here, popping stuff on and off the stack, and then it decides, okay, now I need to call a method, and so its bytecode index is actually going to be captured up here.
Is that where exceptions? How do exceptions work?
Wow.
Very, very quick. You've got to kind of
So it's a more manual process. We're actually going to roll through these frames. This native frame data actually contains a frame pointer, which will point to the frame down here. So you can actually track back through each of the frames. And inside the Java frame data, you can find a reference to the method that's executing, and that will give you access to the exception table for that method. So given an exception of an object of a particular type, you can go through these frames one at a time. Okay, is it getting caught here, getting caught here, getting caught here, and then finally you unroll the stack to the correct place. Yes?
The frame data, the Java frame data, it keeps a reference or an index. But I take it once the method is popped off the frame, it has no reference. Is that true?
The JVM, the question was, is there still a reference to the method once the frame data is popped off? And the answer is that the JVM is always going to keep a variable of its own of what the currently executing method is, because it's going to need to access that very, very frequently. Every time a bytecode gets executed, for example, that accesses a local field, then you're going to have to look up in the method and then find the constant pool and then find where it refers and so on. Yes, Bob?
Is this structure one of the reasons why it's difficult to do tail recursion in the JVM? Or is that kind of...
I got to think about that. Ask me that in a week.
Okay.
You want to know if this is why it's difficult to do tail recursion. It might be. I don't know. Yes?
So you mentioned the locking, that you could lock in one, like at least in concept, right?
Mm-hmm.
So if you could go back and change things about the VM before people started using it to make life easier to implement them, what kinds of things would you be changing?
Okay, so we asked, locking is a good example. Go-to kinds of things also, which are can potentially break out of the block structure of the language. Those are all things that make the JVM implementation much, much more difficult, because you have to handle things, and in particular compilers, because the compiler is going to look at stuff and it's going to say, okay, there's a lock here, so I can pretty much count on a lock and an unlock somewhere down here and then a branch back to someplace else. But the JVM actually says that doesn't necessarily always happen. You can have a lock and an unlock and then a branch, or a lock, unlock and then a branch, and it just makes bookkeeping horrendous.
So what would you, what?
Those would be the two things that I would say right off the bat. And then it gets into the sort of esoteric arguments about whether Java really should be a hybrid stack language, or whether it should be a pure language, or toss the stack altogether and we'll just do stuff the way other languages do. Yes, Cedric.
Are there any fundamental differences between the JVM design and something like the .NET CLR, or are they pretty much like, is CLR pretty much a replica of Java?
I've not looked closely at the bytecode that CLR uses. Perhaps they fixed some of the weaknesses in the Java specification, and so their implementation might be a little simpler, but I got to believe they're essentially very, very similar. Yes?
How does debugging work? Like, do you have to compile differently, or is debugging, are there differences in execution of the same bytecode, or how does that work? I mean, you can't, like, with like loop unrolling, and like it still knows that you're in the loop and what instruction executed it, and other things like it knows you're referencing a variable and not or an object and not a primitive. How does it know that?
So it's all done in bookkeeping. So when you unroll a loop or when you inline a function, or something, all that stuff is kept in data structures, which then, if you're actually using a debugger, then when we actually report what's happening, when you hit a break or whatever, or you break break out of execution, we have to report to you what you think is happening rather than what is actually happening.
So it's actually executing it differently.
Yes, sure. Yep, yep. Yes.
So for the recursive call, is there a threshold on average JVM can handle for calling Stack Overflow?
So I don't actually have it on here, but typically an operating system will provide a way of protecting a page. So when we allocate a stack for a thread, we'll actually protect the topmost page of that stack. So when you start rolling, and the first time you do a write or a read into that protected page, then we'll get an exception and we can report a stack overflow. The downside of that is it's a limited guard area. It's actually a parameter, but typically it's a 4K page in most of the. So if you think about it, if you actually allocate a frame that's larger than 4K and jump right over the guard area, you can actually start munging with other stuff, which you shouldn't be getting into. And that's the kind of thing that causes JVM crashes. Yes?
How does off-heap memory affect this at all, or is that all just in the memory management sort of module?
So the question was, how does off-heap memory affect this? And it really doesn't. That's actually done through. Ding, 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 ding. Oh wow! Here we go. So off-heap is usually done through some sort of class that talks to a native library, which they can then talk to the OS and say, hey, map me another page, and I'll just start using that. And then you have some sort of access stuff that allows you to get in and out of the of off-heap memory. Good. Anything else?
While you have that slide up,
Yes.
what if there's a hardware interrupt that your software needs to respond to? Is that handled in the natives?
Yes, because that would not, in fact, part of this, it's probably in the launcher, it might actually be part of the JVM, I can't remember exactly, but the OS is going to report that as a signal.
Instead of polling.
Right, exactly. So a signal will come up to a signal handler, I think it's actually in the JVM, and then that can be reported to your application.
Can you repeat what the JVM crash?
Oh, sure.
So many things.
I'm taking it you're just interested, right? You're not planning to do this. So if you recall, so we're method I-1 is down here, and they're executing in the operand stack, and they push on some parameters for the next method to be called, and then the JVM is going to say, well, how many locals are in the that are needed by the method that I'm about to call. So if you have a whole slew of large locals, say all double wides, doubles or something, then you can actually jump right over the guard page that's at the top of this stack before you start writing the native frame data. So the next thing you do when you actually do the JSR and you're going to write a return address, that return address is going to go into invalid memory. Yes?
Are there any protections in the compiler to stop you from doing stupid stuff like that?
There are, and it does its best to check, but some things are just, they're legal Java, and so it'll try and trap them before they happen. The interpreter is much better at checking things. The compiler, because it actually compiles things down to, dead fast native code, and strips out all those cute checks that keep us all out of trouble. It's the compiled code that typically will cause that crash. So if you can now consider the compiled method with a whole bunch of loops unrolled and stuff inlined in, and box and unboxes eliminated and dead code cut out, and you run into one of these crashes where some sort of jump has happened and you're off in La La Land trashing memory, it can be real tricky. Yes?
How JVM code is tested?
That's one more time.
How JVM code is tested?
How JVM code is tested. I'm wondering if this is something that I should talk about in the next section. Basically, we have when I was working at Oracle, we had a suite of several hundred regression tests. Every time we made a change to the JVM, we'd run them all, and before any kind of release, it's typical software development, nothing fancy. But every time we encounter a new bug and we fix it, well, you guys know all this, of course, you create a test case to exercise that and make sure that fix is maintained in future versions. Okay, wow. 47 minutes into it, only halfway done. I'm kidding. All right, so this is my lapse into my personal history here. There was a time when, I'm calling it here, dinosaurs ruled the earth. This is, hopefully you'll catch my little theme of evolution that goes through here in the next few slides. But so engineering used to be done in these large organizations in using centralized, cumbersome, bureaucratic processes. And the things that we were testing on, I used to work for the Bell system, and we were testing switching systems. And it was a room full of switching systems, and it cost several $1 million. And so getting testing done and QA done was this crazy bottleneck of people trying to get through the same, single room of gear. So computers used to be, and not just Bell system, not just telephones, but computers used to be that kind of capital intensive in industry. And so that made software development and computer development and technology advancement very, very slow. There were other things, and these still remain a burden for us today. Sometimes there are regulatory requirements for liability, for example. So the Bell system was liable for claims against any of the regional Bell operating companies that came as a result of a telephone outage. So that changed the way they did engineering much more carefully. That's unusual now. When somebody sells a product, software or hardware to somebody else these days, there's no liability take back. It's like you're on your own. If you break something, if you hurt somebody, if you lose property, that's your problem. It's not ours. So I know you guys won't believe this, but I've actually been around long enough to have experienced several of these, what I'm calling extinction events. They're not truly extinctions. A lot of these companies are still around. They're still doing business, but the business has declined significantly. So the first one, the most obvious one, has been the replacement of mainframes by microprocessors. This is old, right? But for me, I actually saw this happen. When I was a high school student, I actually spent 20 bucks of my hard-earned high school money and bought a manual for something called the Selby 8A kit, which was based on the Intel 8008 chip. And I didn't have enough money for the computer, I just read the manual. But things have changed. I mean, and the interesting thing, and the point that I want to make in all three of these examples, is that you really couldn't have seen it coming. Something small. The Intel 8008, believe it or not, was the second generation. It was the 8-bit version of the Intel 4004, which was a 4-bit wide chip, which Intel introduced as a teletype controller. And from there, that started this whole slew. 4004 became 8008, became 8080, became 8086, and then we went 32-bit with 8386. And now we've got these Xeon processors with 18 cores on a die and 64 bits wide. I mean, it's crazy. But for me in high school, thinking that would actually happen from a lowly 8-bit wide chip, it was like, nah, not going to happen. Similarly, the replacement of these big league operating systems is also underway. I was around at Sun when Linux came up. In fact, Sun may single-handedly be responsible or credited with the success of Linux. Sun had actually released a version of Solaris for Intel chips, for white box Intel chips. And people were crazy about it because they could buy their hardware at a fraction of the cost they could get it from Sun. And Sun said, nah, this is cutting into our bottom line. And they discontinued Solaris. I think it was Solaris 8 or x86. And at that time, Linux was really just coming out of the box. And my fellow Sun folks and I, we looked and we said, there's no way. There's no way Linux is ever going to catch up with all the stuff we have built into Solaris. I know, funny, right?
No,
At
all the time.
yeah, exactly. And that's the point of the slide, is you often don't see it coming from very small beginnings. Very significant things can happen. And similarly, you might think I'm actually an industry killer here, but I used to work in telecom too, and telecom was dominated by these very, very large corporations, some of the largest companies on the planet. And slowly they've been overtaken by the ubiquity and availability and bandwidth that's available through the internet. So I recall being in Switzerland, early 80s I think this was, and I called my girlfriend at the time, now my wife, and we spoke for 15 minutes, and it ended up being a $75 charge, which is ridiculous now, right? I mean, we've got Skype, you can do this free from anywhere on the planet. So, you know, things just keep happening.
You should wait until after 11 p.m.
Let's see, did I get rid? Yep, that's it. Anyway, so the point here is that small things can cause tremendous disruption. These big, heavyweight, overblown, bureaucratic, centralized engineering models inevitably crumble of their own weight as soon as a cost-effective challenger comes on board. And so that leads me into meteor showers, get it? Huh? Extinction. It's sad that I have to explain that. Anyway, so things are happening in JVM land. As we've already talked about, the JVM is a complicated piece of code. All the implementations that are around today are done in either C or C++. They're all based on design decisions that were made several generations of hardware ago. And so things, if you actually read the tea leaves, as I'm trying to do here, things are having trouble. So there's been delays in every single Java SE release over the last 3, and I don't even know what happened prior to SE 6, but that may have been delayed as well. So it seems to be coming and you're all nodding your head, yeah, software project always coming late. Yeah, well, yeah, that's true, but I think that's a function of overblown engineering and outdated technology. And I've worked with these people at Oracle, and there's somebody from Oracle. There he is. and the people who work on Java at Oracle are brilliant. They are some of the smartest, sharpest coders in the world. But they're tied down with their process, and they're tied down with what I think is an outdated architecture for the JVM. And another proof point for that is, show of hands, how many people have authored a change to hotspot, OpenJDK hotspot, that has actually been committed? Authored a change to hotspot. Oh, come on, there's got to be one. Wow. Okay, so this is an allegedly open project, right? It's in open source. You can go out there, you can browse the source, you can pick up a bug off Jira and start working on it and submit a fix to Oracle and hopefully it gets committed. Why hasn't anybody of this group of 80 or 100 have ever done this? Yes, Matt.
No, I remember one time I found a bug in the Java compiler and tried to submit a bug and found out you can't even make an account on Jira.
Ooh.
On Jira for OpenJDK.
Okay, I can't fix that.
I think I eventually found they were like, go to the mailing list instead. And I'm like, well, why even bother at this point? I wanted to comment on an existing bug that was similar to the one I had, but instead, they didn't really care.
Yeah, so, well, I think maybe the overall point there is there's tight controls around everything. So that's certainly a barrier, but I suspect that's not the barrier that everybody here is afraid of. Where do you start? This huge, several 100,000 lines of C++ code, all of which is intricately interrelated, and which tweaking one thing causes a problem over here. It's not something that you do casually. You have to really want to do it. You have to really get paid to do it, frankly. So a couple other signs that I think our JVM infrastructure is aging. Oracle, several years ago, embarked on a project that they call Grell. And Grell is some legendary Swedish sea monster or something. I don't know what it actually is, but the old C2 compiler, the optimizing compiler that changes method bytecode into native code, was written over many, many different generations of hardware. When I say hardware, I mean microprocessor design. So those started from very simple, single-threaded, single-core kinds of things to now the things we have now, where 18 threads on a core and hyper-threading and multiple cores in a die and so on. So the C2 compiler, written in C++, has gotten pretty much unmaintainable, to the point now whereas Intel releases, Intel or AMD, releases new changes to their hardware, new features in their chipsets, it takes JVM engineers multiple years to actually get that integrated in because of this crazy C2 compiler issue. We've done the same thing at Azul. We actually beat Oracle to the punch. We replaced our C2 compiler with something based on a project called LLVM, which is an open source project which has got all these cool optimization techniques built into it. It is unfortunately written in C++, but we've actually started doing that. So the point here is that at least two organizations, yes, Phil?
Oh, go ahead.
At least two organizations, I have no idea what IBM is doing, but at least two JVM providers have seen that C2 has got to go. And that's just a sign of, I think, the larger JVM infrastructure.
When Azul did their project.
Yeah.
When Azul did their project.
Yeah.
You would think I would know that Oracle did that, but I had no clue.
Okay.
Did they stop supporting all the old hardware? Did they put a stake in the ground and say we're not covering every piece of hardware?
No.
It was just rethinking the whole architecture.
Correct, yes.
And then going back and applying it to everything.
Yes. Now, the interesting thing about Oracle's Grau project, which is not yet done, by the way, Oracle's Grau project is that their attempt was to implement the C2 compiler in, drumroll, Java. And so their idea, and we're actually getting to my point here, if I ever get there, their idea is that you need to we need a fundamental technology shift in the implementation of the JVM. Not just a rewrite in a couple of places. You need to do something more serious. And here's just kind of a list of some of the hardware innovations that have come over the years since the first JVMs were designed. And all of these have very significant impacts on how the JVM runs. And so here's my commercial pitch for my employer at the moment. So Azul is a small company, but we punch way above our weight. We've actually done some very significant surgery on the JVM and introduced some very cool technology kinds of enhancements. And so our Zing JVM has got, I wince every time our CTO goes out in public and says, we've solved garbage collection. Because I say, somebody's going to come and they're going to kick our butts. But having worked for a bunch of different companies, I can honestly say that this product we have, Azul Zing, is out of the box the cleanest implementation of any product I've ever used. We drop it in dozens of different places at our customers, and it just works. Pretty incredible. Okay, so I'm not the only one who's noticed that there's meteor showers in JVM land. This is actually a paper written by Oracle people saying that adding a feature requires modifying and extending code in numerous locations, intricate dependencies, hard to identify crashes, and VM and compiler research, even to this day, generally addresses performance. We want to get the JVM faster and faster and faster and faster, no matter how much developer productivity time we burn. And that's becoming an increasingly poor investment. And here's another take on the same thing. This is actually a couple years old, but this was a project we'll talk about in just a moment, the Moxie project. Basically saying that the JVM architectures that are out there now were designed almost 20 years ago. So the fundamental design decisions and the design trade-offs that were made in designing Hotspot and J9 and even Zing, frankly, were done a long, long time ago. J9 is apparently actually a derivation of a Smalltalk engine, if you want to go back. So, okay, maybe I stretched the analogy too far. All right, so we'll talk about a couple different projects that, has anybody heard about any of these? Jalapeno, Jikes, Moxie,
I
Matt?
remember Jikes just back in the day when Java was closed source, and seeing Jikes as an option in Linux. I think that was it.
You could actually download a Jikes
Yeah.
implementation? Okay.
Whereas the Sun one was not free, so people kind of tried to avoid
They had to go someplace else, yeah. Yep. Okay, so Moxie was actually instigated by Intel. And there was a project at Apache called Harmony. Maybe you guys have heard of that. It was basically supposed to be a clean room rewrite of a JVM. And unfortunately, they ran into a dispute with Oracle. Well, I think it was actually with Sun. And then ultimately with Oracle, ran into this big legal case that went on for years. Oracle refused to give them license to use the JCK, the compatibility test kit. And so Apache actually withdrew, and to this day remain withdrawn from the Java community. They refused to participate as a result of that little legal spat. Anyways, the idea was we'd get all these top-notch JVM engineers all together in one room and talk about what would it take to make the next generation JVM. And they actually called it the NGVM. And I know a couple of people that were in that room, and this happened in 2005 and 2006. They had two meetings. They mapped out what the next generation virtual machine would look like. The Australian National University took that paper that they produced, and they actually produced a working prototype in 2008. And after that, the project disappeared. The Intel people abandoned it, and everybody went their separate ways. And so I actually, just this past week, sent email to Marcus Lagergren, one of the guys who was in the room in 05 and 06, and asked him what happened to Moxie. And he said, well, they've still got the code somewhere, but the project is essentially abandoned and died. And I'm not sure why. Bears investigation. Anyways, this was, the point here is that in this meeting, all these great JVM designers, all these great JVM minds came to one very interesting conclusion, and that was that the next generation JVM should be implemented in Java, not C or C++. Maxine, which later morphed into the Growl project at Sun and Oracle, was a very similar attempt to design a JVM in Java, written in Java, that would allow experimentation on the different JVM technologies. This is now open source. You can look at it. It's not really a production grade JVM. It was built specifically for research experimentation. So you can, everything is abstracted. Memory models, object layouts, compiler techniques. And so all of that abstraction, of course, comes at a penalty. So this is never going to have any kind of production grade performance. But still, an interesting project. And a JVM written in Java. Jalapeno Jikes at IBM started roughly 2000 or so. Again, an attempt to write a JVM in Java, and they actually achieved a very impressive performance benchmark. Their goal, instead of experimentation and research papers, even though they did, as you see, get a lot of research papers out of it, their goal was to produce a real world performance JVM written in Java. And so they've won some awards. We'll talk about the boot image structure in a minute. The problem here is, at this point, it only runs on PowerPC and Intel 32. So they actually put in a bunch of optimizations that are PowerPC specific And so it would be a significant effort to port this to Intel 64-bit. It is open source, though. And then my own humble effort. I've actually been putzing around with this thing with a very unimaginative name called VMV5, which reflects the number of times I've rewritten it. And at this point, it's just a toy. I mean, it actually executes bytecode. I've got an interpreter in it. It has a very simple memory manager, but it's a fun thing to play with. And of course, it's written in Java, so it's a thought. Anyway, so I know what you're thinking. How do you get a JVM written in Java to actually execute without a JVM underneath it? That kind of defeats the purpose if you have to run a JVM on a JVM, right? So here's Maxine and Jdk both took this approach. They have a host JVM. So ahead of time, take a host JVM, a JVM in Java. You load the class loader. You compile all of or load the class loader compiler and boot file code. Then you load the Java and Java boot file code again, or the startup classes. So the minimum number of classes that you need to actually start up the JVM. We compile them in. And then Maxine and Jdk both use reflection to extract data from the objects that are on the heap, put that into a boot image, a binary file, which can then get loaded up at runtime. And you sort of rehydrate those Java objects, and the JVM can run, starting from native. So that works. You don't actually have to have a JVM to run a JVM, which is a good thing. And then my big idea, and frankly, I thought about this slide for a week. I don't know exactly how to express this. I thought a diagram would be best, but then I realized that it was too complicated to actually put in a diagram. But so let's start here. Java in Java reads in class files like a JVM does, right? And it creates structures on the heap of the JVM that's hosting it. Follow me so far? Okay, so we start here. Host JVM, we start running Java in Java. Let's call it JIJ1.
So
yes?
Host JVM, is that the existing JVM, or is that the JVM that's already written in Java?
This is a find a JVM somewhere.
So that's
this is your cross compiler, sort of.
Okay, so that's not the one that's written in Java.
No, correct. Yes. And any host JVM. Hotspot, Zing, J9, whatever. So pick a host JVM, we load Java in Java, and we execute it. That's our first instantiation of our Java in Java JVM. That one loads Java in Java again, and because it loads things onto its host heap, it loads it onto the host JVM heap. Let's call that Java in Java 2. We start executing. Java in Java 2 now loads the startup class files from Java in Java onto its heap, compiles those methods to native code, fix up pointers, relocate code, do all the twiddly bit stuff to make it right, write it out to a boot file, and now we do the same thing. We have a little native bootstrapper that reads this into the heap and jumps to Java main. Why is this this looks significantly more complicated than the previous one, right? The advantage this has is that it produces all that metadata, all those classes that get read in, they're now in our Java and Java object format. So they're in objects that can actually be manipulated and read by Java and Java itself. So that means that all those cool optimizations that we can roll into client code, we can actually roll into the JVM as well. So if we find that the garbage collector is, it's always calling this one routine to traipse through objects of a particular type, we can inline that. If we've got a fixed duration loop, we can unroll that. All that stuff, all that technology adheres now not just to our client code, but also to the JVM itself. So, my big idea. Anyway, so why are we doing all this? By now, hopefully, you've gotten an idea that I think Java is the right language to implement the next generation JVM in. Here are some of the reasons. Developer accessibility. Nobody here, besides myself, has ever touched hotspot code or JVM code. That's bad. It's open source. It's out there. Portability, the tooling. Everybody is familiar with Java tooling. There's IDEs that exist for it. And then finally, the thing I just talked about, the adaptive runtime, so we can actually optimize the JVM on the fly as it executes and make it faster. As you might guess, there's a whole bunch of technology challenges and a bunch of technology trade-offs. So the JVM, as it's executing, it's Java, right? So it creates objects and it actually consumes memory. So where do we draw the line between our JVM heap, the memory that the JVM uses, and the memory that the application is going to use? Do we draw them from the same heap? Do we create some line in the sand? How much of the JVM do we compile ahead of time, and how much do we compile on the fly? Integrating the Java class library is quite a problem, because the class library, and particularly the native libraries that are associated with it, are all built with the assumption that they're working with a particular JVM, so there's significant porting effort there. Support of these native interfaces would be a problem. Yeah. And then finally, the legal issue that basically killed Apache Harmony still exists. That's still a problem and still unresolved. It's possible that Oracle's a little more, I'll ask Bill.
I'm the last.
It's possible that Oracle's a little friendlier these days. No. Did I say friendly and Oracle in the same sentence?
Larry needs another.
Anyways, that's still an issue. Maybe we can clean room with JCK.
Would you have do you think there would be a concern with, like Oracle has indicated they're going to continue on with their API litigation against Google? I think they came out like 2 or 3 weeks ago. I mean, doesn't that make you a little unnerved about implementing something in Java? Because then, I mean, it's sort of incestuous. Like, you're feeding back onto that, and how could that ever be open source? Like, if they make that same claim on API ownership, I mean, isn't that sort of a slippery slope into saying?
Well, the JVM is deliberately specified through a JVM specification. And the idea is that anybody who can meet that specification by whatever means produces legal code, right? Produces a legal product. So the fact that we're all going to do this, right? The fact that we write our JVM in Java and it meets a JVM specification, as long as we can prove that we didn't draw any intellectual property out of Oracle, we're safe, right? Phil? Yeah, Bob.
That you also have to pay for the test compatibility kit. So I mean, to call something Java, you have to get a license from Oracle.
Yes.
I am certifying this as Java, and that is kind of where the stack of that.
Yes, there is a trademark issue. Is that what you were after?
Sort of the same. Also,
okay, I thought it was a technology thing, but yes. There's a trademark issue. In order to call something Java, it has to pass the Java certification kit. And in order to pass the Java certification kit, you have to be licensed to use that. And at this point, the only thing that's licensed to use the JCK are works that are derived from Open JDK, which this wouldn't be. So yeah, so it's a problem. Anyways, so it's a work in progress, gang. Yes, Matt, one more.
Wouldn't this technically not really be a problem if people just embraced the GPL and actually just used it instead of trying to make more permissive versions of the JVM?
Not an attorney. Sorry. Anyway, so hopefully you got the drift of this. You got an idea how the JVM works, what it's supposed to do. Hopefully you're at least concerned about the technology path that existing implementations of JVM are on. Hopefully you also believe the JVM experts, not just me, not that I'm one, but the JVM experts that met in Project Moxie and decided that the best way to implement a new JVM is, in fact, in Java. And this, in fact, I think is the way forward. Yeah, there's problems, but I think we got to push them. Anyways, so it's my intent, since this is a work in progress, to report back to this august body at some point, maybe, I don't know, a couple months from now, I'll do a lightning talk and let you know what else I found out. But I'm still working on this and still researching. So, all right. Finally, questions, discussion, anybody? Yes?
If you run a JVM in a JVM, doesn't that increase your startup time significantly?
Sure. Yes, but the whole point of this was that running the JVM in the JVM in the JVM was to produce a binary boot image that then boots up very, very quickly.
Oh, so you'd end up with a binary that started from Java that you can keep.
Correct. Yeah, so everything's compiled down, everything's pre-parsed, and you load the whole thing into a chunk of memory, and then you can just jump to the entry point in compiled code, and it just runs.
So how does this work? You install JVM first, and then you install the JVM and JVM on the computer, and this like actual practical implementation.
Practical implementation would be there'd be two primary components. Obviously, there'd be more than these, but two significant components. You have to have the native bootloader, which is actually very similar to the Java program that we now execute, which actually loads in the libjvm.so. So the bootloader would then take this big binary file, wouldn't have to be that big, I guess, big binary file, load it into memory, and then branch to it, and you'd be running JVM.
Just before you take any other questions, if there's any questions, just repeat the questions for...
Yeah, we also have this catch box here too.
Oh,
So,
yeah, where'd it go?
We want to do the catch box. We throw it to whoever wants to go.
Okay, Freddie just said to repeat the question. Oh, sorry. Go ahead.
So, Al, you can repeat the question. So you mentioned on one of your slides symmetric or like sort of SMD
Yep.
and GPU compute.
Yep.
Are there any specific challenges as it relates to doing that with the JVM, or is that something that like the Zool projects address?
Well, there's a different compiler for each, right?
Yeah.
It's a different native code, so you'd have a little more work to do. But in principle, as long as there's some synchronization and some sort of memory share between the host processor and the GPU processor, should also work. Yeah, I don't see any technology barriers. Yes, Matt. Sorry, I forgot to repeat your question. I'm so bad.
Has there been any thought on implementing JVMs in something besides C++ or Java? Like, for instance, I know, I forget who, I think it was Facebook or Microsoft, use like OCaml, for instance, to write a compiler, like, or using maybe more functional language, or maybe going with like Rust or something new, like that might be easier to work with or more performant.
It's an interesting question. The question was, has anybody thought about doing it in anything other than C, C++, or Java? And by doing it, I mean implementing a JVM. Not that I'm aware of. The research papers that I've seen have all been JVM and Java.
I think there's like a toy JVM in Golang, just like a GitHub project and so on.
Oh, okay. Yeah. Cool.
Oh, Golang.
Yeah. Yes.
So if you wrote a JVM within a JVM, wouldn't you have issues with the existing garbage collection underneath the JVM? Wouldn't that cause interference?
Well, so the JVM within the JVM actually has to allocate its own heap. And my little toy JVM just allocates a big old honking array of ints and uses that as its heap. And it does have to do its own garbage collection, so yes. So the host JVM has its own heap, and then the guest JVM has objects that reside on that heap, and then one of those objects is actually its own heap. Yes?
So the JVM and the JVM, if you're doing JNI, do you have to drill down through all the turtles to get to the operating system?
Yes, you do. Okay. I don't think I was clear. The question was, with JVM within a JVM, do you have to drill through multiple layers to get to JNI? Yes, you do. However, the deployment structure is not a JVM within a JVM. It's a pre-compiled, preloaded JVM in binary form, which does not have its host JVM underneath it anymore. It's a bootstrap. It's been extracted out of the relevant heap and put into a binary file, and now it's ready to run on its own.
So you'd still be dependent on whatever that originating JVM was for new hardware architectures that came out in order to like interpret what's coming from the OS. That's what I'm trying to understand. Like, because you would always need to recompile on that underlying JVM, your JVM.
Yes, but the host JVM, it's sort of like a cross compilation. So the host JVM allows us to compile down our JVM into the relevant binary code for the target machine. You could actually do it for a different machine. That target code never actually executes when you're doing the JVM on the JVM. It's simply compiled, it's set out there, you extract it, you put it in a binary file, then you can transport it over to a completely different machine architecture and run it.
So it's similar to like if you've ever worked with Golang, being able to compile like a Mac OS binary for the Darwin kernel from a Linux box. That also works.
Right. Yes.
You're changing the definition of like write once, run anywhere. Slightly,
Okay.
right? So right now I compile once, it will run. My jar will run.
Yes, yes, but because it's compiling down to native code,
Totally
right,
understand.
it's machine specific, correct. Yep.
But if you transport to a different machine, that machine still has to have a host JVM, correct?
No, no need.
You're writing with blob.
It reads,
Yeah.
it reads the host JVM to write it out like.
Right. It's basic. It's easiest to think of it as a compilation step. You're taking Java code in which you've written a JVM, and you're using this elaborate thing that I've described here to compile it down to native code.
Yeah.
And then once you're in native code, that's a standalone JVM.
Yeah, it's sort of like a incomplete analogy, but like when you build a Gradle, like when you run a Gradle build, you load a JVM to compile your Java code, but you're not relying on the JVM that Gradle is running to run.
Absolutely right. Yes, and lots of IDEs run that way too. There's a JVM that runs the IDE, and then there's a JVM that runs your code. So, anyways. All right.
Yeah. One more question? That's it?
Quick run!
He's going to trip again. You know that. These are like marble stairs, and I think somebody spilled a beer on it. All right. Paul, thank you so much.